All right, the topics for today are electronegativities and bond polarity, VSEPR theory and molecular shapes, and types of molecules. We're going to start off with taking a look at a hydrogen molecule made up of two hydrogen atoms. Here's our Lewis structure for it. And these two atoms, because they have the same number of protons in the nucleus, are going to pull at the shared electrons with the same attraction. So we have equal sharing of electrons. And this is going to wind up giving us a non-polar covalent bond. And non-polar means no charge is formed. So if we were looking for the electrons in this molecule, where would we most likely find them? Well, since they're pulling with an equal attraction, they'd probably spend more time between the two than they would spend around either one of the atoms. Now, if we compare this molecule with one made of two different atoms, hydrogen and chlorine, and you notice that in the drawing, the chlorine is darker around it than there is a hydrogen, and this indicates that the shared electrons are going to be pulled closer to the chlorine and spend more time around the chlorine. And this is not shown at all when we draw the Lewis structure of it, so we need some more data for that. So we're going to have an unequal sharing of electrons, and this is going to wind up giving us a polar covalent bond. Now, in order to determine this, we need to have some data, and so we're going to use electronegativities. So the electronegativity is the ability of an atom to attract towards itself the electrons in a chemical bond. And atoms vary on their ability to attract electrons. And so if we look at the numbers from the electronegativity chart, we would have 2.1 for the hydrogen and 3.0 for the chlorine. So the chlorine has the stronger attraction for the shared electrons than the hydrogen does. Because of this, the chlorine is going to become a little bit negative and the hydrogen a little bit positive. And these Greek letters mean partial. So we wind up getting partial charges on the atoms in the molecule. Partial means something that's less than a 1. So it's not -1 and +1, but it's some fraction of that. Now here's an electronegativity chart. There's one similar to this in your book. And what we want to note is that the higher numbers are to the right and the lower numbers are more to the left over here. So metals have low abilities to attract electrons. And as you go to the right, the ability increases somewhat. Notice there are some metals here, some common metals with a pretty good ability as well. But that tells us that some of their bonds might be more covalent than ionic. We're going to see that coming up. So we're going to be using these electronegativity values to determine whether the bonds are polar, nonpolar, or ionic. And to do that, we need to know what does the difference mean when we subtract them. So here's a chart that we're going to use. If we have a zero difference between the electronegativities when we subtract them, then that's going to give us a true nonpolar covalent bond. So that means we have true equal sharing and there are no charges whatsoever. More than likely, though, we're going to have some difference in the electronegativities. When the difference is very slight, like maybe 0.1 or 0.2, the charges might be present, but they're so weak that they don't have really any effect. So we're going to still call that a nonpolar covalent bond. But remember, there are some charges present. Now, as the difference continues to grow, the charges get greater in strength. And we're going to just arbitrarily throw out this number. We're going to say once the difference is greater than 0.4, the bond is more polar covalent than it is nonpolar. And over here, this kind of indicates the same thing. Ionic character means the strength of the charges. And covalent character means the weakness of the charges. So as the electronegativity difference grows, so do our charges. And eventually, the charges get strong enough to become full +1, -1 or so. And that gives us an ionic bond. So we're going to say an ionic bond is formed when the electronegativity difference is greater than 2.0. So let's check out some now in an example. So here's a problem where you're asked to find the which type of bond do you have in these three different particles. I'm saying particles because CSCl is not a molecule. And what we have to do is just simply look up the electronegativities. And so the first one we look up is for the cesium and the chlorine, 3.0 and 0.7. Now if we subtract these, we get a difference of 2.3. And if you look that up in the previous chart, you'll see that 2.3 means that it's an ionic bond. Now we would have known that anyway because cesium is a metal. It's way down here, down near the bottom. And chlorine is way over here, non-metal. So that just reinforces what we already suspected. Now if we take a look at the second one, HBr, we have hydrogen and bromine, and the difference is 0.7. and that's going to give us a polar covalent bond. And then for the NN bond, well, both of these have the same electronegativity, so the difference is 0, and that's a true nonpolar covalent bond. So it's going to be as simple as that. Now I want to take a look at the shapes that molecules form. Now we're really just talking about small molecules. Large molecules have no particular shape. And with a large molecule, when you look at it and try to find little areas, that'll indicate what kind of molecule it might be. So we're just going to focus on small molecules. Now we're going to be using the VSEPR theory, which stands for valence shell, electron pair, repulsion theory, in order to figure out the shapes. Now the central atom will be the key to doing that. And we're going to be asking the question, does a central atom have any lone electron pairs or not? So this is number one, we're going to check that out. If the central atom has no lone electron pairs, then the bonded atoms, the atoms that are bonded to that central atom, will rotate as far away from each other as possible. So again, central atom, no lone electron pairs, then the bonded atoms rotate as far away from each other as possible. This means that you have to draw the Lewis structures correct in order to know this. So you might want to review that. And secondly, if the central atom has lone electron pairs, then the lone electron pairs repel the bonded atoms towards each other. This is going to give us what we call an asymmetrical shape, whereas in number one, we'll get symmetrical shapes. So let's take a look at some of those now. First of all, for symmetrical shapes, so there are three of them that you have to know. First one is called linear, and linear is anytime you have three atoms bonded together, it could be linear. Now linear here means that that central atom that get no lone electron pairs, so these two atoms get as far away from each other as possible. So that's called linear. Now the second structure we're looking at is called trigonal planar, where the atoms occupy the same plane. Now in this situation, we have three bonds from that central atom, as you can see here, the three atoms bonded to it. And the central atom again has no lone electron pairs, so these three atoms have moved as far apart from each other as possible. And the third one we have down here is called tetrahedral. Here we have a central atom with four electron pairs all involved in bonding. And you can see that represents carbon and our four hydrogens. So these are nice symmetrical shapes. And again, the key, this is central atom. Let's take a look at some others now. And we'll go by that one. Okay, let's take a look now at number two. Here we're talking about the central atom having lone pairs. And you see over here we have A, and it has two bonds, but it has two pairs of electrons not used in bonding. That causes these atoms to get closer together than they normally would. It gives us that asymmetrical shape, which we're going to call bent. Now, two electron pairs causes it to get closer than one, but they still are going to be an asymmetrical shape. The other one you have to know is called trigonal pyramidal. And here we have one atom bonded to three, and we only have one lone electron pair, as you can see here. And these guys are forced closer to each other. So it's called pyramidal because it kind of represents what a pyramid looks like. This would be at the apex of the pyramid, and these guys would be at the basis. So let's check out ammonia here, NH3. We've drawn that a lot this year. So here is ammonia. Here's the nitrogen atom here. And here we go. The nitrogen is bonded with three hydrogens. And here's that lone electron pair. And I have the dots right in here. So this shape would be pyramidal. And if we check out water, we have the oxygen atom here in the middle, two lone electron pairs. And we have our bonding pairs here. Here are two bonding pairs. And you can see the hydrogen atoms in there. And that's going to be a bent shape. And now in summary, we take a look at them then. The shapes would be tetrahedral, trigonal pyramidal, and bent. Now, let's see if you can draw these guys out. Draw out the structural formulas and then determine the shapes. So you might want to pause the screen at this point and check that out. I'll come back later and see it because I'm going to go through the answers then now. Okay, so here they all are. The HBr would be linear. Anytime you have just two atoms bonded together, the shape is always linear. When you draw out pH3, you wind up with that phosphorus with a pair of electrons there, not used in bonding. And that's going to give us this asymmetrical shape called trigonal pyramidal. When we do CCl4, carbon tetrachloride, the carbon is bonded to all those chlorines. There are no lone electron pairs. That's going to give us a tetrahedral shape. Now when you draw out CO2, and I've left out these dots, but what you want to see is that the carbon has no lone electron pairs. So these two oxygens will be as far away from each other as possible, and that's going to give us a linear shape. It doesn't matter that they have double or single bonds, it's going to be a linear. Now if you compare that to SO2, SO2 is bent, and that's caused by these lone electron pair on the sulfur. It's going to be key for the property, so you've got to be careful with this one. Now compare SO2 to SO3. There's no lone electron pair in SO3, so what happens? These three atoms rotate as far away from each other as possible, and we have the shape called trigonal planar. Now we're going to put all that information together. In order to figure out what type of molecule you might have, we have to know what kind of bonds there are and the shape. So the first type of molecules we can see are called dipoles or polar molecules. They must contain polar covalent bonds. Then they will have asymmetrical shapes, which will cause them to have charged ends. So these polar molecules can look like little magnets, and thus they attract each other. Now the second type of molecule we can have would be called nonpolar. And a nonpolar covalent molecule may contain nonpolar covalent bonds. And if it does, that's all you need to know, and it's a nonpolar molecule. But it may also contain polar covalent bonds. If it has a symmetrical shape along with polar covalent bonds, what we're going to see is that the little charges that are there on the molecule will cancel each other out. So this is where it's a little tricky. So it's possible to have a nonpolar molecule that contains polar covalent bonds, and then the shape decides what it is. So let's take a look at a molecule. This is hydrogen fluoride. So we have electronegativity difference that is pretty high. The difference is 1.9. So the fluorine is a little bit negative, and the hydrogen is a little bit positive. And what that means is that electrons are drawn towards the fluorine. That's what this arrow is showing. And so we're going to have electron-rich area and electron-poor area. Now when they talk about polar molecules, the term dipole moment is used a lot. And it's just a way of measuring how polar one molecule is versus another. And so we're going to see a list of them in a table here. So these are the dipole moments. You don't have to worry about how they calculate them all. I just want you to notice that if we look at these, let's check out these first four. They're all just linear molecules, and this hydrogen with all these halogens. And we get fluorine, HF has the highest dipole moment. That means it is the strongest charges. And as you go down the list, the charges get smaller here. If you were to compare these to the electronegativity differences, you would see that HF had the greatest difference and the HI had the least difference. And then if we check out H2O and H2S, both bent molecules, and they're both polar molecules now, you notice that the water has the stronger charges. This kind of shows you that charges are due to, these dipole moments are due to the shape and the type of bonding. And so here we have three molecules, methane, ammonia, and water. Now, what type of molecules are these? Well, let's say the methane contains nonpolar covalent bonds. The electronegativity difference was 0.4. And tetrahedral shape, because the bonds are nonpolar, the molecule is nonpolar. Now, I want to point out, what if the bonds had been polar? Well, it wouldn't have mattered even if we had slight charges on the hydrogens, because the charges would have been all the same, and they wind up being canceled out because the charges are surrounding the carbon. In order to have a polar molecule, the charges must be concentrated in one area. So all the positives on one side and negative on another. So even if these bonds were polar, the molecule would be nonpolar. Now when we check out ammonia, we find that we have these charges on the molecule. Each of the hydrogens becomes a little bit positive, and the nitrogen a little bit negative. That's because of the electronegativity differences. Now, if you notice, the electrons are being drawn in the same direction, all towards the nitrogen. So this tells us that we have a polar covalent molecule. So we have polar covalent bonds, pyramidal shape, and it's a polar covalent molecule. We have all the positive charges concentrated down here and the negative up here. If one of these hydrogens had been up here so that they were surrounding the nitrogen, the molecule would have been nonpolar. Now we look at water. Electronegativity difference is pretty high. We get our charges in. Electrons are all being drawn towards the oxygen, so they're reinforcing each other. And so we're going to have here another polar covalent molecule or a dipole. So we have polar covalent bonds, a bent shape which is asymmetrical, and thus a polar covalent molecule.